Today we'll complete the study of determinant and its properties, and so we'll discuss three more important applications of the notion of the determinant. And so the first would be 8.10, Cramer's rule. This is a way to write down an explicit formula for solutions of a linear non-homogeneous system with a non-degenerate matrix. So let us formulate a corresponding theorem and prove it. Let A be a square non-degenerate matrix. Then the solution of a non-homogeneous system A multiplied by x equals b is given by the formulas x sub j equals delta sub j divided by delta, where delta is the determinant of the matrix A, and delta sub j is the determinant of the matrix obtained from A by removing its jth column by the right and by replacing its jth column by the right-hand side. So we have A sub 1, 1, A sub 1, 2, etc., B sub 1, and etc., A sub 1 n, A sub 2, 1, A sub 2, 2, B sub 2, etc., A sub 2 n, etc., A sub n1, A sub n2, n2, etc., B sub n, A sub n n. So here we replace the jth column of our matrix by the right-hand side. So the theorem states that the solution of the system can be given by these explicit formulas. So J ranges from 1 to n. Let us prove this theorem. Since A is non-degenerate, the solution is unique, as we know. Consider the reduced row echelon form of the augmented matrix of this system. So we start with the initial matrix, then we apply elementary row operations, and we get the matrix, the identity matrix at the left-hand side, just because our matrix is non-degenerate. So the reduced row echelon form of any non-degenerate matrix is the identity matrix. So this happens when we apply elementary row operations. And The important thing is that when we apply these elementary row operations to our augmented matrix, both delta and delta sub j are transformed in the same way. Elementary row operations affect in the same way on delta and on delta sub j. Either both are preserved or both are multiplied by the same constant. And this means that their quotient is preserved. So such quotient is preserved when we apply elementary row operations. So it is enough to prove this formula for the transformed system, just because they are equivalent. For the transformed transformed system, which takes the form the identity multiplied by x equals b tilde. And this transformed system is always equivalent to the initial one. But for the transformed system, this is more or less obvious. So why? Let us look at what happens when we consider the transposed system. So we have this identity matrix here. Then we multiply it by the column of unknowns, and we get the right-hand side. So this means that x sub j is just b sub j tilde, where j ranges from 1 to n. And on the other hand, what is delta? So delta is 0. Delta is 1, just because it is the determinant of the identity matrix. And delta sub j is the determinant of the matrix where the jth column is replaced by the right-hand side. So this is the determinant of the form 1, etc., b1 tilde, etc., b j tilde, b n tilde, and then 1 on the principal diagonal, and 0 is everywhere. So this is also b sub j tilde. So we see that for the transformed system this is obvious, and this proves the result that we stated. So sometimes it is important to have this result just because it gives us an explicit formula for solutions of such a system, but in practice this is not very convenient to use this system for solving systems with to use these formulas for solving systems with more than 3 variables, just because in this case we need to compute determinants of the 4x4 determinants. It is much easier to use elementary row operations in this case. But anyway, these formulas have theoretical significance, and sometimes they are used in theoretical purpose. Fine. So this is one of the applications that we discussed today, and the second one is the relation between the rank of the matrix and its minors. So 8.11, the rank and minors. So here we are also going to formulate and to prove one theorem. So let A be a matrix with n rows and m columns. So we do not require this matrix to be a square one. Then the rank of A equals R if and only if R is the maximal order of a non-zero minor of the matrix A. So we need to prove that if the matrix A has the rank R, then there exists an R by R non-zero minor, and we need to prove that this is the largest size or the largest order of a non-zero minor of this matrix. So first of all, let R be the rank of A. So this means that there exist R linearly independent columns of this matrix. So let me denote them by the column with the number j sub 1, the column with the number j sub 2, etc., the column with the number j sub r. So we assume that these columns are linearly independent. Consider the matrix A tilde, which has n rows and r columns. That is constructed from the selected columns of A. So what do I mean? We have this A tilde. So its first column is the column of the matrix A with the number j sub 1. Its second column is the column of the matrix A with the number j sub 2, and so on. So this is how we construct the matrix A tilde. So the rank of this matrix is also R, just because it consists of R linearly independent columns. That's why there exist R linearly independent rows of this matrix with numbers, with row numbers I sub 1, I sub 2, etc., I sub R. So consider the matrix A with two tildes constructed from these rows. Then its determinant is non-zero, just because these rows are linearly independent, and the determinant of this matrix is exactly a minor of the original matrix of the order R. And so the determinant of A with two tildes is an R by R minor of A. So this proves the existence of a non-zero minor of the order R. So this is the first part of the theorem. And now we will need to prove the second part of the theorem. So assume S is greater than R, where R is the rank of the matrix, and S is not greater than the minimum of the number of rows and the number of columns of the matrix A. Consider an S by S minor of the matrix A. So let this minor be constructed from the elements in columns with numbers j sub 1, etc., j sub s, and in rows with numbers I sub 1, etc., I sub S of the matrix A. So this means that all other columns and all other rows of this matrix are removed. So we consider this matrix. So this is the matrix A, and so we remove. So we keep only the columns with the numbers J1, etc., Js, and the rows with the numbers I1, etc., Is. So what is on the intersection of these columns and these rows forms the S by S minor that we consider. So it consists of the elements that are on this in these positions of the matrix A. So we know that the columns of our matrix with numbers J1, etc., Js are linearly independent. Sorry, are linearly dependent. Since S is greater than R, which is the rank of our matrix. As before, construct the matrix A tilde from these columns. The rank of A tilde is not greater than R. Therefore, any S rows of A tilde are also linearly dependent. Hence, the determinant formed by the rows of this matrix with numbers I1, etc., Is is 0. And this determinant is an S by S minor of A. So we have chosen an S by S minor where S is greater than R, and we show that this minor is 0. So this proves the theorem. And this theorem is very important for various applications in different fields of mathematics, particularly in calculus or in differential geometry. So that's why we need to clearly understand what happens here. And then the last of the applications of the determinant is the so-called the Vandermonde determinant. So this is some particular determinant that is used in different situations, and that's why we need to discuss it. So let us give the definition. Let x1, etc., xn be distinct variables. Then the determinant of the following matrix. So this is the matrix that has, this is nn by n matrix, which has 1 as the elements of the first column, then x1, x2, etc., xn, then x1 squared, x2 squared, etc., xn squared, and so on, x1 to the n minus 1, x2 to the n minus 1, etc., xn to the n minus 1. So the determinant of this matrix, which will be denoted by the capital of x1, etc., xn, is called the Vandermonde determinant. And now we will deduce the general formula for the Vandermonde determinant. So the theorem states that v of x1, etc., xn equals the product where I is greater than j of the elements of the following form: x sub I minus x sub j for every n natural n. So this determinant can be represented as this kind of a product of the differences of coordinates. So let us prove this theorem. Maybe it's better to say that n ranges not from 1 but from 2, just because it is not clear what is this determinant for n that equal 1. So of course we can say that it is just the determinant of the matrix that consists of the only element that is 1, but maybe it's better to say that n starts from 2 here. So let us subtract from every column of this matrix the previous column multiplied by x1. So this is one of the elementary column operations, and such operations do not change the determinant, so let us look what happens. So v of x1, etc., xn equals the determinant of the matrix that has the form, so the first column is preserved, and then we have 0 here, 0 here, and so on. So we have only zeros in all other elements in the first row, just because in every column we subtract x1 to the k from x1 to the k, when we do these elementary row operations. And so what are we going to have in the columns, in the rows below this zero, below this row? So here we're going to have x. So I need more space. So I will remove these zeros and then I will write them for the second time. So the second column has the form 0, then x2 minus x1, then let's say x3 minus x1, and so on, so xn minus x1. So these are the elements in the second column. Then in the third column I'm going to have 0, then x2 squared minus x2 by x1. So etc. xn squared minus xn by x1, and so on. And so the last column has the form xn to the n minus 1 minus xn to the n minus 2 by x1, and so on. xn it should be x2 here, x2, and xn to the n minus 1 minus xn to the n minus 2 multiplied by x1. So this is what we get here. And since we have 1 here and the row of zeros here, this determinant is equal to the determinant of the block that is in the lower right corner of this matrix. So we just get the determinant of the matrix that is here, and I'm going to simplify the elements of this matrix. So I have x2 minus x1 here, then I have x2 multiplied by x2 minus x1, etc. x2 to the n minus 2 multiplied by x2 minus x1. So the next row will have the form x3 minus x1, x3 by x3 minus x1, and so on, x3 to the x3 to the n minus 2 multiplied by x3 minus x1. And so all the rows will have the same structure. Here we're going to have xn minus x1 multiply. Here we're going to have xn multiplied by xn minus x1, and so on, xn to the n minus 2 multiplied by xn minus x1. So this is the determinant we get. And now we can observe that all the elements in the first row have the factor of the form x2 minus x1. So this determinant, so we can just put this factor out of the determinant. So this determinant is divisible in some sense by this factor, and the same works for all the rows of this matrix. So we can simplify this determinant by writing that it is equal to the product x2 minus x1 by x3 minus x1, etc. xn minus x1 by the determinant of the matrix of the form 1, etc. 1. Then we have here x2, x3, and so on, xn, and x2 to the n minus 1, x3 to the n minus 1, etc., xn to the n minus 1, n minus 2, sorry, it should be n minus 2, because we have n minus 2 here. So this is what we get, and we come to the conclusion that the determinant of the original matrix has the form where we have the product of n minus 1 factors of this form by the Vandermonde determinant of the variables x2, x3, and so on. And now, using the principle of mathematical induction, we can state that that our statement holds true for every n, just because if n equals 2, then obviously the Vandermonde determinant is x2 minus x1, which is exactly the product that we have here for n equal to 2. So the formula holds true. Therefore, by induction, the formula holds true for every n starting from 2, just because here we have, according to the statement, here we have the product of all factors of the form x sub I minus x sub j, where I is greater than j, and both are greater or equal, and so j is greater than or equal than 2. So here we have all factors of this form starting from 2, and here we have all possible factors that include x1. And that's why when we consider all these factors, we get the product of this form where j range from 1, just because here all the factors that include x1 are outside of this determinant. So when we multiply these factors by the determinant that is formed by the variables x2, x3, etc., xn, we get exactly the product of this kind. So this proves the theorem. And this theorem will be widely used for proving that some families of functions are linearly independent. We'll discuss this later. These are the three applications of the determinants that I plan to discuss today, and so we will now finish to discuss the determinants, and we will move to some other topics. So we'll discuss some algebraic structures that will be important for this course. So the next section, section number 9, Interlude 2, algebraic structures. And 9.1, groups. These algebraic structures are not specially related to linear algebra, so they have general significance in mathematics, but so we will widely use them, and that's why in order to make this course self-sufficient, we will say a few words about the definitions and basic properties of groups, rings, and fields. So these are algebraic structures that we are going to use within the frame of this course. And so that's a typical thing for different algebraic structures, that they are defined by a number of, each of them is defined by a number of axioms, and these axioms are of course selected not at random. They are taken as the properties of some existing object, and so the basic idea is to generalize some existing object and to formulate a definition, to formulate some abstract definition such that this existing object is a particular case of some general structure defined by a number of properties. And so we will see how it works on the example of a group, of a ring, and of a field. So let us start with the definition. Let G be a set and let dot be a mapping from the Cartesian product of G by itself to G. So this means that this dot, this operation, takes two elements from the set G and maps this pair to some element from G. Then the pair G and this operation is called a group if the following properties are satisfied. So G1 A dot B dot C equals A dot B dot C. This means that in the left-hand side we first apply this mapping to the pair of A and B, so we get some element from the set G, and then we have another pair and we apply our mapping to this pair, so to the result of applying the first mapping and to the second. And so here we do this in this order, and in the right-hand side we first apply our mapping to this pair, we get some element from the set G, so we have another pair, and then we apply our mapping for the second time. And so the requirement is that these two elements of the set G should be the same. So this is called associativity. This property is called associativity. Then G2, there exists an element E from our set G such that G dot E equals E dot G equals G for every G from G capital. So this means that when we apply this mapping to a pair where G is the first argument and E is the second, we always get G, and the same happens if we apply our mapping to another pair, to the pair where E is the first argument and G is the second argument. So and G3 for every G from G, there exists element G to the minus 1, so it is just a notation, such that G by G to the minus 1 equals G to the minus 1 by G equals E. So we require that these three properties should be satisfied, and if they are satisfied for some set with some operations of this kind, then this set is called a group. So this pair is called a group, or we just can say that G is a group with respect to the operation dot. And so let me also say that the element E from the definition is called the identity or the neutral element. And g to the minus 1 is called the inverse for g. As we will see, the identity element and the inverse for every element for every element of a group are uniquely defined. So let us prove this. Proposition that G dot be a group then the identity element is unique and for every G from G, the inverse is also unique. The proof is quite simple, but before we start the proof, I would like to mention that in most cases this dot is just omitted. So we just write GE, assuming that this means that we apply this operation dot to the pair of elements G and E. And so since we have in mind something like multiplication, in general, people just say G multiplied by E. So let us prove that the identity element is unique. So suppose there exist two elements E and E tilde that satisfy the property G2. Then let us start with E tilde. So it is some element from our group. That's why it can be represented as E tilde multiplied by E. So E is the so the element E satisfies this axiom. So if we take E tilde instead of G and apply this axiom, so we get this relation. So since E is the identity. But we also know that, according to our assumption, E tilde is the identity. That's why when we multiply some element by E tilde, we should get this element. So this is E. So the second relation follows from the fact that E tilde is the identity. So it is quite simple, but we can deduce the fact that E tilde equals E just from the axioms. So here we apply the axiom to the element E, and here we apply the axiom to the element E tilde. So this proves the first part of the statement, and now let us prove the second part of the statement. So consider G from G capital and assume there exist G to the minus 1 and G to the minus 1 tilde that satisfy the property G3. Then G tilde inverse can be represented as G tilde inverse multiplied by E. So this follows from the fact that E is the identity. So it follows from the property G2. And then, since we know that G and G to the minus 1 without a tilde are inverse to each other, we can represent this as follows. So G tilde to the minus 1 by G multiplied by G to the minus 1. So here we use the axiom G3. So we apply this property to the element G. So the product of G and G to the minus 1 should be equal to E. Okay, and then we're going to use the associativity property. This is G1. So this is equal to G tilde to the minus 1 multiplied by G and multiplied by G to the minus 1. And now we observe that the element that is here is exactly the identity, just because we suppose that G tilde is one of the inverse elements to G. So we get E multiplied by G to the minus 1. So here we apply the third axiom. And now we can once more apply the second axiom, G2. So here we multiply by the identity. That's why we get G to the minus 1. And so this chain of relations shows us that G tilde to the minus 1 equals G to the minus 1. So this proves that the inverse element is unique for every element from a group. So this is quite trivial, but nevertheless, these arguments show how to use these kind of definitions. So we just use the axioms one by one, and this definition is quite abstract, so we have absolutely no idea about the origin of this set. It could be a set of any nature, and if these properties are satisfied, then we can deduce some other properties from these basic properties from the definition, from the axioms of the group that are listed in the definition of a group. And so one more definition. A group G dot is called commutative or abelian if A multiplied by B equals B multiplied by A for all A, B from G. So the group is called commutative if the result of multiplication of two elements does not depend on the order in which we multiply them. So this is kind of additional axiom. So sometimes it is important to consider groups without this property, and sometimes it makes sense to consider abelian groups, that is, groups with this additional property. Okay, so let's now consider some examples. So the first example would be one of the basic examples for the notion of a group. So consider the set of all integer numbers and the operation plus. So this is just the addition of numbers. So this pair is an abelian group. So we know that the addition of integer numbers satisfies the property of associativity and commutativity. And so what is the neutral element? So here 0 is the identity. So y, any for every integer number n, we have n plus 0 equals 0 plus n equals n. So here we replace dot in the definition by plus because we have plus here. And so plus is a mapping that assigns some element from the set of integers to every pair of elements to every pair of integer numbers. So we have the identity element, and for every n, the inverse is minus n. So indeed we have minus n plus n equals n plus minus n equals 0. So this is what we get here. Okay, that's why the set of integer numbers is a group with respect to addition. Then the second example, the set of natural numbers with respect to the same operation is not a group. So it is not a group because there is no identity element if we define the set of natural numbers starting from 1, because in some countries people define the set of natural numbers starting from 0. In this case we will have the identity element, but we will not have the inverse to any element different from 0. So in both cases, in both possible definitions of the set of natural numbers, this is not a group. So I will not comment on the second way to interpret this, but so I will not write this. I just said a few words. Okay, then in the same way we can consider other sets of numbers. So the set of rational numbers is a group, and the set of real numbers is also a group with respect to addition. So I will not go into the details, just because here everything is exactly in the same way as in the first example. And I will just make a remark. Sometimes the group operation is denoted by plus, as we did it here, and we will see later why do we need this. And in this case, the identity element is denoted by 0, as we did it here, and the inverse is denoted by minus j. The inverse to g is denoted by minus g, as we did it here. And by definition, if we use this notation, then a minus b is a plus the inverse to b. So this is the definition of the operation minus in such a group. So a minus b by the definition is equal to a plus the inverse to b. So this form of the group is also sometimes used, as we see here, and that's why sometimes we will use the notation with dot, and sometimes we will use the notation with a plus. And so I have already mentioned that sometimes dot is omitted, but plus is never omitted if we use this notation. So we see that in some sense the definition of a group is copied from the definition of the set of integer numbers. So maybe it's better to say that the definition of an abelian group is copied from the definition of the set of integers, just because we pick the properties that are satisfied for any integer numbers, properties like associativity, like the existence of the neutral element and the existence of the inverse and the commutativity. And so we say that any set satisfying these properties is called an abelian group. That's why the notion of the abelian group generalizes, in some sense, the particular case of the set of integer numbers. And we can study all sets G with these properties, and sometimes it makes sense just because we can formulate some properties, we can prove some theorems for all sets with this structure, and that's why we can use them later for any particular set satisfying this structure. So we prove some theorem for all groups, and then we can use these results for some particular group. So it could be a group of integers or any other group. Okay, these were the most trivial examples, and let me consider some more examples. So example number 4. Consider the set of all permutations of n elements. So denoted by Sn. So when I introduced permutations, I used the word the symmetric group. So now we will see that we can introduce the structure of a group on the set of all permutations, and so this group will be called the symmetric group. So we define the multiplication of two permutations as we did before. So this is the composition, in fact, because every permutation is a mapping, so we just take the composition of these two mappings. Then there exists the identity element, so this is the permutation that leaves all the elements where they were. So this is just the identity mapping, and for every element sigma from this set, there exists the inverse. So we have already discussed this, but we just did not use these words. So the group Sn, so and maybe I'll use the composition, is called the symmetric group. So we have one more example of a group which is not a subset of the set of real numbers. So this is a group, and note that this group is not abelian. If n is greater than 2. So indeed, consider two permutations. So sigma 1 would be a permutation of 3 elements of this kind, and sigma 2 would be a permutation of this kind. Then sigma 1, sigma 2 is what? So let us multiply the two permutations in this order. So what are we going to get? So here 1 goes to 1, and then 1 goes to 2, 2 goes to 3, then 3 goes to 3, and 3 goes to 2, then 2 goes to 1. So this is what we get here, and sigma 2 multiplied by sigma 1 is the product of these two permutations in the reverse order. So what do we get here? So 1 goes to 2, and 2 goes to 3. Then 2 goes to 1, and 1 goes to 1. 3 goes to 3, and 3 goes to 2. So we get two different permutations. So obviously this group is not commutative. Then two more examples. So example 5. Classes of residues. So let P be some natural number, P's, and let P be greater than 1. So consider an equivalence relation on the set of integer numbers. So m is equivalent to n if the difference between m and n is divisible by p. So this is really an equivalence relation, and the classes of and the equivalence classes are called residues modulo p. Modulo p. So consider two classes. M and N, so I will denote the classes in brackets. Then we can define an operation on the set of these classes. So M plus N, by the definition, is the class of the element M plus N. So this definition obviously does not depend on the choice of representatives. So why? If M is equivalent to M tilde and N is equivalent to N tilde, then M minus M tilde is equal to K multiplied by P, and N minus N tilde is equal to L multiplied by P for some L and K, for some K and L. And then M tilde plus N tilde is what? So it is M minus K P plus N minus L P, which is M plus N minus K plus L multiplied by P. So we have that. So we get that the sum of the elements M tilde and N tilde is equivalent to M plus N. So they belong to the same classes, and so that's why this operation is well defined. So we have this kind of operation on the classes of residues and denote the set of all classes by Zp. So this Zp is the set of classes of 0, 1, etc., p minus 1. So it consists of p elements just because the class of p is the same as the class of 0. So we have p elements in this set, and this set is a group with respect to the addition, is an abelian group. So the commutativity and the associativity are obvious, but so what is the identity element? So the class of 0 is the identity element, and for any class M, the class of the element p minus n is the inverse. So just because according to our definition, the class of n plus the class of p minus n, according to the definition, is the class of n plus p minus n, which is the class of p, which is the class of 0. And so we see that the classes of residues form an abelian group. So it's a finite abelian group. So all the groups that we had here are infinite, and here we have two examples of finite groups. And one more example. So geometrical vectors, I will call it. So consider vectors on a plane. So we can add vectors. I will not go into the details just because this is very simple. So this is the sum of the two vectors, right? And so geometrical vectors form a group, or better to say an abelian group. With respect to addition. So this is how we add two vectors. The 0 vector is the identity element, and the vector minus a is the inverse to a, just because a plus minus a is the 0 vector. So that's quite trivial, but we see that. And of course, the associativity and commutativity are always satisfied for geometrical vectors, and so that's why they form a group. Of course, there are many more examples of groups. We have no time to discuss and no need to discuss more examples. And instead of this, we will define two more algebraic structures that will be important for our considerations. So 9.2, rings. Now I'm going to define one more algebraic structure. So let R be a set, and consider two mappings plus and dot, which act on the Cartesian product of, sorry, not G, in this case we consider, we denote the set by R. So two mappings from the Cartesian product of this set to itself. So a triple R plus and dot is called a ring. If the following properties are satisfied. So the first property, R1, R is an abelian group with respect to the first operation. Then R2, A plus B multiplied by C equals A multiplied by C plus B multiplied by C, sorry. And R3, A multiplied by B plus C equals A multiplied by B plus A multiplied by C for all A, B, C from the set R. So the properties R2 and R3 are called right, left distributivity. So now we have two different algebraic operations, and the relation between these two operations is defined by the distributivity properties. So, and if these properties are satisfied, then this set is called a ring with respect to these two operations. And so I'm going to make a remark. If R plus dot is a ring, then the identity element with respect to plus with respect to the first operation is called the additive identity and is denoted by 0. And the inverse with respect to plus is called the additive inverse. And is denoted by minus a, the inverse to a with respect to the first operation is called the additive inverse. And is denoted by minus a. And by the definition, as we have already mentioned, a minus b in this case will also denote the sum of a and the inverse and the additive inverse to b. So these are some remarks concerning the definition of a ring. And now let us prove a number of statements that are satisfied for any ring. So let R be a ring with respect to the two operations. Then the following properties are satisfied. So the first property, a multiplied by the additive identity equals 0 multiplied by a equals 0 for any a from the ring. Then a multiplied by minus b equals minus a multiplied by b equals minus a multiplied by b for any a b from R. And the third property, a multiplied by b minus c equals a multiplied by b minus a multiplied by c, and similarly a minus b multiplied by c equals a multiplied by c minus b multiplied by c for all the elements from this ring. So let us prove these statements. So the first statement, so in fact we have two different statements here. Let us just consider one of them. The second one is proved similarly. So denote a multiplied by 0 by b. Then what is b plus b? So b plus b is a multiplied by 0 plus a multiplied by 0. Just follows from what we denoted here. And then we can use one of the distributivity properties. So here we have 0 at the right, so we use the second property. So according to the property R2, we get sorry, not to the property R2, but to the property R3. So we're going to use the distributivity property R3. And according to R3, this is A multiplied by 0 plus 0. And then, using the fact that our ring is an abelian group with respect to the first operation, 0 plus 0 makes 0 in this abelian group, so we get A multiplied by 0, which is B. So we get the relation that B plus B equals B. Okay, and then add minus B to both sides of this relation. So what do we get here? We get B plus B, then plus minus B equals B plus minus B. So here once again we use the property of addition, so all the properties of the first operation are hidden in the first axiom. So this is the additive identity, which is 0, and on the other hand, we're going to use the associativity property, which is also included into R1. So this would be B plus minus B. Once again, we're using this property. So here we get B plus 0 according to this axiom. And once again, we're using this axiom. This is B just because we add the additive identity to B. So B equals 0. So this proves that B equals 0, and the second statement is proved similarly. So the second property, consider A multiplied by minus B plus A multiplied by B. So according to the property R3, so we have here the factor A at the left, so according to the property R3, that is equal to A multiplied by minus B plus B, and so according to the properties of addition in the ring, this is A multiplied by 0 by the additive inverse, and this is 0 according to the first property, according to what we have already proved. And so we see that A multiplied by minus B is the inverse for A multiplied by B. And since the inverse is unique, we come to the conclusion that A multiplied by minus B equals minus A multiplied by B. So the second statement is proved similarly. And now the third statement. So once again, we're going to prove only one of them because the other one is proved similarly. So consider A multiplied by B minus C plus A multiplied by C. So once again, we use the left distributivity, so it is denoted by R3. So we get A multiplied by B minus C plus C, which is, according to the properties of addition in the ring, it is equal to A multiplied by B plus 0, which is A multiplied by B. So here we also use the properties of addition, and now if we add the inverse to this element, we get what we need. So now we have this property, and now we add the inverse to A multiplied by C. So what do we get? We get A multiplied by B minus C plus A multiplied by C plus minus A multiplied by C. So using the associativity, so I will not go into the details just because we have already done this. So this is A multiplied by B minus C on one hand, and on the other hand we just use this relation. So we get A multiplied by B plus minus A multiplied by C, and so this is A multiplied by B minus A multiplied by C. So this proves the relation that we had, that we need. And so the second relation is proved similarly. So this proves our statement. So these properties are satisfied in any ring. And now, before we go to examples, let us make a few remarks. So if A multiplied by B equals B multiplied by A for all elements in the ring, then the ring R is called commutative. If A multiplied by B multiplied by C equals A multiplied by B by C for all A, B, C from R, then R is called associative ring. Sometimes this property is included into the definition of a ring, but I decided to take the most general definition without this requirement. So, a ring could be commutative, associative, and if there exists such element, so I will denote it by 1. So if there exists an element 1 such that A multiplied by 1 equals 1 multiplied by A equals A for every A from R different from the additive 0, then this element is called the multiplicative identity. So not every ring has the multiplicative identities, so this is not included into the definition of a ring, but some of the rings, as we will see, have multiplicative identities, and so similarly to the case of a group, one can prove that if this multiplicative identity exists, then it is unique. So the proof is exactly identical to the one we already had. So these are some additional properties that are satisfied for some rings. And so let us consider some examples. So the first example is quite trivial. So all sets Z, Q, R, so the sets of integers, rational numbers, and real numbers are rings with, or better to say, are commutative associative associative rings with the multiplicative identity with respect to the operations plus and multiplication. So that's quite trivial. It follows from the properties of elements in these number systems, and we see that the notion of the ring, the definition of a ring, is in some sense copied from the definition of from the properties of the set of integer numbers. So it generalizes in some sense the set of integers. So another example. So the set of all even numbers which is denoted by 2 multiplied by z, is a commutative associative ring without the multiplicative identity, just because obviously the element 1 that should be a multiplicative identity is not in this ring. Then the set of all polynomials with real coefficients or with rational coefficients, this makes no difference. forms a commutative associative ring with the multiplicative inverse, or the multiplicative identity, sorry, one which is just the constant polynomial. So p of x is identically equal to 1. So if we multiply this polynomial by any other polynomial, we get this non-zero polynomial. Then another example, the set of all n by n matrices with real coefficients is also an associative but not commutative ring. We know that matrices do not commute in general with respect to multiplication, so this is an associative but not commutative ring with the multiplicative identity, which is just the identity matrix. And finally, the last example of a ring, the set of residue classes is a commutative associative ring with the multiplicative identity. So we need to define the second operation. So how to multiply the classes of residues, the set ZP. So we define the multiplication exactly in the same way as we defined the addition. So this is the class of the element n multiplied by m, and this definition is also independent on the choice of the representatives in these classes. And so obviously this operation is commutative, associative, and the multiplicative identity is defined as the class of element 1. So obviously it satisfies the definition. So we have a number of examples of rings, and so all of these examples are very important. And now let us consider the last algebraic structure for today. This is the structure of a field. So 9.3 fields. So I'm going to start with the definition. So a commutative associative ring with the multiplicative inverse, with a multiplicative identity, is called a field. If every element A different from 0 has a multiplicative inverse. So this means that there exists the element a to the minus 1 such that a multiplied by a to the minus 1 equals a to the minus 1 multiplied by a equals the multiplicative identity. So in this case, this ring is called filled. And so we will denote fields by blackboard bold F. So this would be a standard notation for arbitrary field. Okay, before we go to examples, let me give one remark that one may define a field in slightly another way. A field as a set F with two operations plus and multiplication, which act on the Cartesian product of F. So as a set satisfying the following relations. So F1. So F is an abelian group with respect to the first operation. So the second property is that F without the multiplicative identity is an abelian group so the set without the additive identity is a group with respect to the second operation, is an abelian group with respect to the second operation, and the distributivity property, so A multiplied by B plus C equals A multiplied by B plus A multiplied by C for all elements A, B, C from this field. So in this case we do not need to add another distributivity property just because the multiplication is commutative, so the second distributivity follows from the first one. So we can define a field in this way. And so I will also need to make a remark that in a field the multiplicative inverse is unique for every element A from the field. So this is proved similarly. Similarly to what we did for groups. So now I'm going to prove one very important property that is satisfied for fields but is not satisfied for rings. So let F be a field. Then if A multiplied by B equals 0, then either A equals 0 or B equals 0. So this is what we need to prove. So assume A is not 0. Then, according to the definition of a field, there exists the inverse, so A to the minus 1, such that A multiplied by A to the minus 1 equals A to the minus 1 by A equals the identity, the multiplicative identity. Okay, then B can be represented as B multiplied by the by the multiplicative identity. Right? So this follows from the properties of the multiplicative identity, and so I can rewrite this as B multiplied by A multiplied by the A to the minus 1. So this is the way to write down the multiplicative identity, and so this is B multiplied by A to the minus 1. So here I'm using the associativity property, and now I'm going to use the commutativity property, A multiplied by B by A to the minus 1. And so we know that A multiplied by B is 0, so we get 0 multiplied by A to the 1, and according to the property, to one of the properties of a ring, so this is 0. So we conclude that if A is not 0, then B is 0. So similarly, we can conclude that if B is not 0, then A is 0. So this proves the claim, and so I will make a remark on this. So the elements A and B such that A multiplied by B equals 0 are called zero divisors. So we just proved that in a field there are no zero divisors. There are no zero divisors. But in a ring, there could be. So this is the most essential difference between a commutative associative ring with the multiplicative identity and the field. So in such a ring there could be zero divisors, but not in a field. And this is very important. And so let us consider some examples. So the first example shows that the set of rational numbers and the set of real numbers are fields with respect to the addition and multiplication and the standard multiplication. But the set of integers is not a field. Since there are no multiplicative inverses for all elements different from plus and minus 1. So the ring generalizes the set of all integer numbers, but a field generalizes the set of rational numbers and the set of real numbers. And in the same way, the set of all polynomials is not a field. And just because a non-constant polynomial has no inverse, has no multiplicative inverse. So the set of all n by n matrices is also not a field. Because a degenerate matrix has no multiplicative inverse. And finally, the last example. Consider the classes, the residue classes, Zp, where p is a prime number. Then Zp is a field. So, indeed, we already know that for any p, Zp is an associative multiplicative ring with the multiplicative identity, so we only need to show that any non-zero element has the multiplicative inverse. So, for any residue class, consider integers n and p. It follows from Euclidean algorithm that there exist U and V such that N multiplied by U plus P multiplied by V equals 1. So it follows from the Euclidean algorithm, and so consider the residue classes. So here we get the class of N multiplied by the class of U plus 0, just because the class of this element is 0, equals the class of 1. So the class of U is the multiplicative inverse for the class of N. And this is not true if P is not prime. So consider Z6, for example, then the class of 2 multiplied by the class of 3 equals the class of 0. So we have 0 divisors, and this is not possible in a field, as we just proved. Okay, so we have a number of examples, and we see that the notion of a field generalizes the case of a field of real numbers, and the most important thing from our point of view is that all rules of arithmetics that we are accustomed to by working with real numbers are satisfied in every field. For example, we can do simplification using distributivity or using associativity, or we can change the order of factors using the property of commutativity. Then we can cancel the factors using this property, which is not possible in a field. So if the product of two elements is 0 in a field, this means that at least one of them is 0. So this works in every field, as we proved. So everything works in the same way as in the case of real numbers. And this means that many things that we did, or maybe it's better to say that all things that we did before with matrices, with linear systems and all that, can be extended to the case of arbitrary fields. So we can consider matrices with entries not from the set of real numbers, but with entries from an arbitrary field. And we can multiply matrices, we can add matrices where multiplication and addition are understood as multiplication and addition in a field. So we can define the multiplication and addition of matrices where elements are from the fields in the same way as we did for matrices with real entries. Then we can consider linear combinations. We can prove all the properties about linear combinations, linear dependence, linear independence exactly in the same way, because all we needed for this were the properties of real numbers. And these properties are contained in the axioms of a field, so they also can be used for any they can be used for any field, and that's why we can repeat all these procedures for any field. So all the statements about linear dependence and linear independence are satisfied for vectors of the coordinate space f to the n, which extends the case of a coordinate space r to the n to the case of arbitrary field. So it is possible to extend all these notions to the case of arbitrary fields. Besides, it is possible to consider systems of linear equations with entries from arbitrary field. Just because we multiply them, we add them, and this is possible. It is possible to do it in any field. And all these statements about the properties of linear systems are also satisfied for linear systems with coefficients in arbitrary fields. So this is done absolutely in the same way. So we can use we can use Gaussian elimination and all that. So it works exactly in the same way. That's why all these statements that we proved before can be generalized to the case of arbitrary fields, and that is the most important thing. And so the next thing that we will do, not at the next lecture, because the next lecture will be another interlude, but after that we will define the structure of a linear space that generalizes the structure of a coordinate space, and in this case we will use just arbitrary fields. So in most cases, in this course, we will use arbitrary fields. There will be, of course, there will be some restrictions on the fields sometimes, but nevertheless, in most cases, all the statements will hold true for arbitrary fields. And so that's it for today.